So in this class, we will discuss a problem on laterally unrestrained cantilever. So how we can design a laterally unrestrained cantilever beam. This is an examination problem BTU January 2020. So the data given is like this: span of the beam is 5 meters, bearing width 100 mm, dead load 20 kN per meter, live load 10 kN per meter. The beam is encased into a concrete wall, that means it is fixed at one end, and free at the top. Free at the top means it is laterally unrestrained or unsupported. That is the mean. So the solution looks like this. So dead load is given 20 kN per meter, live load 10 kN per meter, total load is 30 kN per meter. So design load will be 30 into 1.5 cost effective factor. So 45 kN per meter. So now this is the diagram. 45 kN per meter is taken as the WU. So maximum bending moment in this case will occur at A, it is M, and maximum shear force also will occur at the fixed end, which is B. So maximum bending moment is given by WU L square by 2. If you substitute L as 5 and W as 45, so you get 562.5 kN per meter M value. And maximum shear force B is W into L, which is 45 into 5, 225 kN. Now we have to design a section in such a way that the design bending strength of the section MB should be greater than M, and design shear strength VD should be greater than B. So now, for that to have the preliminary design, we have to calculate ZPZ required. So ZPZ required is taken as 40% more than what is required for laterally restrained beam. That is 1.4 times this value. So here the guideline is you can take 25% to 50% more. So I have taken here 40% more. So because the span is more, 5 meter span for a cantilever beam, definitely it will give larger deflection. So therefore I have taken 40% more. So it's only trial and error. If I take 1.4 into M value is 562.5 into 10 power 6 Newton millimeter into gamma M is 1.1 divided by 250. F is 250. If you simplify, you will get ZPZ required as 3465 into 10 power 3 millimeter cube. Now from the steel tables, you can choose ISWB 600 at 133.7 kg per meter with ZPZ 3986.66 into 10 power 3 millimeter cube. Slightly more than this. You can choose slightly more than this. Now this is the geometrical dimensions of that particular section. So total overall depth is 600 mm, width of flange is 250 mm, TF with thickness of flange 21.3 mm, radius of R1 is 17 mm, DW thickness of flange is 11.2 mm, ZEZ, the elastic section modulus is 3340 into 10 power 3 mm cube, IZ, moment of inertia about the ZX is 106198.5 into 10 power 4 mm 4. IY is moment of inertia about this vertical axis, y axis 4702.5 into 10 power 4 mm 4, and D is the depth of web, which is given by H minus 2 times TF plus R1. If you substitute and simplify, you get 523.4 millimeter as the value of D. Now, the third step, after choosing this wide beam, so ISW Indian standard wide beam section, that is the name of lecture. So section classification we have to check because as far as possible try to keep the section as plastic or compact. So we have to check according to table 2 page 18 of IS 800. So we have to check both for flange and web. For the flange, we have to consider the ratio B by TF. B is half of BF, so which becomes 125 divided by TF is 21.3. Ratio is 5.87, which is less than 9.4 epsilon, where epsilon is this constant root of 250 by Fy, where Fy is 250, epsilon becomes 1 here. So it is less than 9.4 epsilon, that means it is a plastic section. So flange is plastic according to the table. Then web, to check for the web, I have to take the ratio D by TW. D is 523.4 divided by TW is 11.2. If you simplify that 46.7, which is less than 84 epsilon, which is also plastic. Since both brand and well for plastic sections, the entire section is taken as plastic or class 1, and the value of beta B is taken as 1. So that is the section classification. So it is okay. Now third step is computation of the MCR value, which is the elastic critical lateral buckling moment in the case of laterally unrestrained beams. So this is given by the formula which is given in page 54. MCR is equal to root of pi square E Iy by LNT square into GIT plus pi square E IW by LNT square. So if you substitute the values, E as 2 into 10 power 5 Newton per meter square for steel, G as 76,923 Newton per meter square, and LNT as 5,000 mm. So we require two more parameters, that is we require this IT and IW. IT is called as the torsion constant, which is given by sigma BI by 3 for that particular section. So there are two flanges here, so 2 times. So B for the BI for the flange is this BF, which is 250, into TI for the flange is TF, which is 21.3 cube divided by 3. Because there are 2 flanges, we have to multiply it by 2. Plus for the web portion, we have to take H minus TF as BI. So which comes out to be 600 minus 21.3, which is I think we have to take 571.4, 574.1. I think there is slight change here, please check that. Into 11.2 whole cube by 3 as that TI value for web is 11.2. So if you simplify, you will get a value nearly equal to this. That is the torsion constant whose units is millimeter power 4. Now for this IW, this is called as the warping constant, which is given by a formula in page number 129. So 1 minus beta f into beta f into I by h by square, where beta f is 0.5 for symmetrical sections. Here in the I section what we have chosen is symmetric, beta f becomes 0.5 into 0.5 into I y value for that assumed section is 4702.5 into 10 power 4 into hy is this, once again hy is this value, I think slightly, this is 600 minus 21.3. So it comes out to be 578.7. So please make that correction. 578.7 it will be. So slight variation will be there. Please make that change. So slight variation in this value. So if you simplify, this value will be in millimeter power 6 because IY is in millimeter power 4, HY is in millimeter. So millimeter power 4 into millimeter square becomes millimeter power 6. Slight variation may be there. Please check that. Okay. Then once you get IT, IW value, you know E value, G value, LNT as 5000 mm, substitute in the equation 1, get the value of MCR. Simplify that. You are getting, I think slightly, you may get a slight different value. 1302.12 into 10 power 6 Newton millimeter. Then using the same page, that is page 54, you have to calculate certain parameters, non-dimensional slenderness ratio, lambda at, so which is given by root of beta b to z into fy by MCR. So everything should be in Newton and millimeters. Please you have to note that beta b is 1 because it's a plastic section, into z is whatever you have provided, 3986.6 into 10 power 3 into fy is 250 divided by whatever MCR you have got there, that you substitute, you will get a value here, lambda lt, one value you get. If that value is greater than 0.4, then we have to consider the effect of lateral buckling, you have to consider. That is very important. Anyway, here also you are going to get the value greater than 0.4. Then another parameter phi nt, 0.5 to 1 plus alpha nt to lambda nt minus 0.2 plus lambda square nt. So here alpha nt depends on type of section. For rolled section it is 0.21, for welded section it is 0.42, double of that. But here it is a rolled section, ISW is a rolled section, so you have to take 0.21, and whatever you have got here, the lambda NT value, you have to substitute and simplify, you will get another value 5 NT. Then xi NT, one more parameter, 1 divided by 5 NT plus 5 square NT minus lambda square NT to the power 0.5. If you substitute the values and simplify, you will get a value here. Almost it is less than, you make it less than 1. So that value xi NT you will get. Then after getting that, you have to calculate a very important, that design bending stress. Design bending stress, xi NT Fy by gamma MO. So whatever xi NT you have got there, that you substitute here into 250 Fy divided by gamma is MO is 1.1. If you simplify that, you will get the value of your BD Newton per meter square. Then finally, you are going to get the value of design bending strength MD, which is given by your BD into ZPZ into beta B. So beta B is 1 here, ZPZ is whatever you have provided, 3986.66 into 10 power 3, in the FBD whatever you have got here. So substitute and simplify, you will get the value of MD Newton millimeter. Later on we can convert it to kilonewton meter. So the check is that whatever MD value you are going to get, it should be greater than maximum bending moment M. Of course, in this case you will get it. So maximum bending moment is 562.5 kilonewton meter. Obtained is somewhere here is nearly equal to this. So it will be greater. So that means it is safe against bending. That is the meaning. Now you have to check whether it is safe against shear. And another thing is MD value should be less than a certain ratio as per the code. So I will just write that. So it is available in same page, in page 54. After calculating this MD value, you have to check whether the MD value is less than or equal to, you have to check this. Let's check here, check for MD value. Once again it is in page 54 of the code IS 800. So this MD value should be less than 1.2 ZEZ into Fy by gamma MO. This you have to check. So let us check that. 1.2 into ZEZ is 3340 for that ISWB 600 into 10 power 3 into 250 divided by 1.1. So whatever you get that, so it is 910.91. 10.91 into 10 power 6 Newton millimeter, or it is 910.91 kilonewton meter. So definitely your MD value is here. Whatever you have got 668.7 something you have got, please check that for that value. You may get slightly different, slightly less value. You can see that this is greater. Since this value is greater than this, so therefore okay. So this is check we have to do. Then after this, we will check for shear. Shear check is done. So check for shear. Next is check for shear. Next step. So I am doing the complete design. So sixth step. So check for shear, we have to calculate point VD we have to calculate. Then we have to check whether that whatever value of V is there, that V is less than 0.6 VD. So VD is equal to, according to the formula given in the code, so VD is equal to Fyw divided by root 3 gamma MO into H into TW. This is for hot rolled section. So once again, it is available in the page number. I will tell you. So it is there in the code. The last problem also I had given the explanation for this. So it is available in page number 59 of the code. So we have to calculate this value. So in this case, FYW is for the web portion, same 250 we have to take, divided by root 3 into 1.1. This multiplied by H is 600 into TW is 11.2. So that is the area of the web, gross area of the web. So if you simplify that, you will be getting 881.77. So kilonewton, of course, we are getting in Newton into 10 power 3. So it becomes 881.77 kilonewton. So this is the value of BD. BD is the design shear strength of the web. Then once you get that value, compare the 0.6 times BD with the V. V is the maximum shear force which acts at the fixed end in the case of cantilever beam. So here V is 225. You know that here maximum shear force is 225 kilonewton. Now you take 0.6 times BD. 0.6 times BD is 0.6 into 881.77, which is nothing but 529.06. 529.06 kilonewton. Now you can observe that this V is less than 0.6 times BD. So this is a case of low shear. So that means there is nothing to worry. Therefore, safe against shear. So this is how you have to check for shear. Then after this, seventh one, web buckling. Let's check. Web buckling is done only if the ratio of T by dW is greater than 67 epsilon. So let us check only if. So d by dW we have already calculated. In this case, I think while doing that section classification, we have checked for d by tW, and that value here is d by tW value is 46.7. So which is definitely less than 67 because epsilon is 1. Therefore, web buckling check not required. It is safe. Check not required. So next is we have to check for web bearing check. So bearing check we have to do. So once again, that is available in code, that equation which I had explained in the last video also. So that is the last one. So we have to check for bearing. So which is available in page number 67 of the code. Bearing. So check for web bearing. So last one, 8th step, check for web bearing. So whether it is a simply supported or cantilever or any beam, if bearing check is asked, so here of course in this case he has given the width of bearing as 100 mm. Even if he has not given, you can assume bearing width as 100 to 125 like that. So here it is given in the problem. Not given also you can assume 100 mm. The corresponding equation is so FW is equal to B1 plus N2. So please refer page 67 of the code, 67 of IS 800. So FW is equal to BN plus N2. FW is equal to B plus N2, B1 plus N2 into TW FYW by gamma MO. So you need to remember any formula, everything is available in the code. So this is the formula. B1 is this value, width of bearing given. If it is not given, you can assume 100 mm. Plus N2 is nothing but the dispersion width. So which you have to take normally it as 2.5 times. 2.5 times that half of that whatever width is there. So that means you can take it as half of the depth. So 2.5 times 300. So that is the dispersion width. Into TW is 11.2 here. Into FYW is 250 divided by 1.1. So whatever value you get here, it will be in newtons. So this check is whatever this local capacity of the local capacity we can say. So it should be greater than the maximum shear force. So check is FW should be greater than V. Then it is safe. So now I think you can check that if you are getting greater than this 225 kilonewtons, then it is safe. Okay, so I think you can check it 100 plus 2.5 into 300 will be it is 750, 850. So 850 into 11.2 into 250 divided by 1.1. So it comes out to be very high value. I am going to get 2163636 Newton, or you can take it as 2163.6 kilonewton. Definitely it is greater than B, so nothing to worry. Therefore, okay. So this is how we have to check for that bearing. So the entire complete design is done like this, but in the examination, if they ask you to check only for moment capacity, you can find out MD, and if you prove MD is greater than M, that is there is the matter. If they ask you to check for shear, you have to do check for shear. Then if they ask you have to do check for bearing and buckling, then you have to do that. So this is the complete design of the cantilever beam, which is laterally unrestrained, which is given in the examination.